High Peak Courses are a British Government registered learning provider with the UK RLP.
Hello, I'm Warren Leigh. Welcome to High Peak Courses.
This free introduction to the design and analysis of structural composites is suitable for student and graduate engineers who have little or no knowledge of engineering composite materials.
Lecture 4. An Engineer's Start. In this Lecture 4, we will look at the composite properties of a layered composite. We will start with a simple two-layer unidirectional glass fibre composite. Next, we will introduce the tailoring principle of stiffness and strength by examining a carbon fibre composite containing a number of angle ply layers. That is, single plies laid at an angle of 45 degrees and minus 45 degrees, known as plus minus 45. These examinations are to demonstrate the effects on the mechanical properties of a composite by adding angle plies to this laminate. Towards the end of the lecture, the initial size and stress analysis of two simple beams will be made using the composite properties that we have designed in this lecture. Using simple structural elements of beams, cantilevers, pressure vessels, etc., the initial design analysis, sizing and weight determination, and hence ballpark cost of many complicated structures can be evaluated prior to doing any expensive finite element analysis and test.
Here we'll look at the initial design and sizing of structural composite components. We will examine tailored strength, tailored stiffness, tailored weight, the composite laminate properties you will need to know before you can start a design. And I will look at two examples of carbon fibre properties and glass fibre properties. The most important number that tells you if your composite design will work. And two examples, one is a box beam example and the other is a channel beam.
The challenge in this task is for an engineer to design a cost and structurally viable composite component. I will examine two types of layered composite materials. That of glass fibre and the other composite of carbon fibre. For simple geometric component designs, and even more complex ones such as rocket cylinders or main structural parts such as wing spars, an initial design and composite component sizing can be accomplished by using classic hand calculations. A finite element model may be used later to refine the results of the analysis, or if the component has complex geometry. We start designing the laminate architecture by first determining the Young modulus of our selected layered composite. A simple composite laminate in a resin, also known as a layup, consists of two layers of unidirectional glass fibre fabrics. This means that the fibres of each layer run in direction 1. Our material axis of fibre direction 1 aligns with the geometry reference axis of X. One layer of unidirectional glass fibre is placed on top of the other layer. Next, we require glass fibre material properties. I'm going to use published data. Unidirectional glass fibre composites gives a Young's modulus in the x direction 1 of 40,000 newtons per millimetre squared. Young's modulus in y direction 2 of 4,000 newtons per millimetre squared. Ultimate strength in the x direction 1 of 1100 newtons per millimetre squared. The ultimate strength in y direction 2 of 400 newtons per millimetre squared. And the thickness per layer is calculated in CSAMs of 0.096 millimetres. In this initial design process, for sizing a composite component, we start by determining the equivalent Young's modulus of our designed layered composite. Calculation of layered glass fibre composite properties. For the glass fibre composite properties, we will use CSAMs, which is Composite Structural Analysis Modules. Click on MSAMs. Now the centre section of the form is generic material properties that I have built into the software. For now, the centre section can be ignored, but it can be changed if necessary. Start by selecting the top left drop-down box. This is the fiberglass box for unidirectional material at 120 GSM. Its corresponding box on the far upper right, type in the number 2 for 2 layers of unidirectional glass fibre. All the boxes below, set them to the value of 0, as we don't require any of the other materials for this calculation. Press Calculate button at the right-hand bottom of the form. You will now see the results given in the boxes in the lower half of the form. The CSAM software gives us the following composite properties. The equivalent Young's modulus EXM equals 40,000 newtons per millimetre squared. Equivalent Young's modulus EYM equals 4,000 newtons per millimetre squared. The equivalent Young's shear modulus GXY that's 1112 newtons per millimetre squared, and the total thickness of this composite laminate is 0.192 millimetres. Now the strength of this composite is based on strain limitation, and CSAMS calculates the strength in direction 1 at 160 newtons per millimetre squared. Strength in direction 2 equals 16 newtons per millimetre squared, and the shear strength equals 4 newtons per millimetre squared. Now, based on these calculated composite material properties of equivalent Young's modulus, strengths and thicknesses, an initial size of the intended composite component can now be calculated. Please note that the EXM and EYM means EX in membrane and EY in membrane. Notice in this glass fibre composite that the equivalent Young's modulus does not change. This is because the fibres are all aligned in the same direction. The strength, however, is strain limited. So now we look at the calculation of a layered carbon fibre composite. We're looking at determining the properties. We include layers of carbon fibre that have orientations to the direction axis 1. So these are angled plies. The strength of the cured composite and other composite properties are affected by the orientation of the layers. This is the basis of tailoring. There are other reasons for designing a composite with different orientations, such as manufacturability and minimum weight, for example. So now we do a calculation of the properties of a layered carbon fibre composite. A carbon fibre composite laminate, also known as a layup, consists of a total of 5 layers of carbon fibre fabrics in a resin matrix. Number 1. The bottom layer is 120 GSM woven fabric of fibre direction 45 degrees and an equal number of fibres in the direction minus 45 degrees. This is known as a plus minus 45 degree. Number 2. The next fabric layer is 100 GSM unidirectional carbon fibre aligned in direction 1, or as referred to in the diagram as the 0 direction. Our material axis of fibre direction 1 aligns with the geometry reference axis of X. Number 3. The next layer is 120 GSM woven fabric of fibre direction 1 at 0 degrees and an equal number of fibres in the direction 2, that is 90 degrees. This type of fabric we call a 0-90. Number 4. The next fabric layer is 100 GSM unidirectional carbon fibre aligned in direction 1, or as shown in the diagram as the 0 direction. Number 5. The top layer is 120 GSM woven fabric of fibre direction 45 degrees and an equal number of fibres in the direction minus 45 degrees. This is another plus minus 45. So the laminate we have is symmetrical about the middle layer, and this is shown by the red dotted line. Next, we require carbon fibre material properties. I will use published data, and this is embedded in CSAMs. Gives a Young's modulus in the x direction, i.e. one direction, of 135,000 newtons per millimetre squared. In the next example, y direction 2 of 11,000 newtons per millimetre squared.
The ultimate strength of the unidirectional carbon fibre in direction 1
is 1,400 newtons per millimetre squared. The ultimate strength in y direction 2 of 140 newtons per millimetre squared. The thickness per layer in CSAMs is given as 0.098 millimetres. For the carbon fibre composite properties, we will use CSAMs. So click on the MSAMs button, go to the carbon fibre section, start by selecting the left drop-down box. This is the carbon fibre box for the unidirectional 100 GSM. The corresponding box in the far upper right, type in the number 2 for 2 layers of unidirectional carbon fibre. All of the boxes below set to the value 0, as we don't require any of the other materials for this calculation. Press the Calculate button at the right-hand bottom of the form. You will see the results given in the boxes in the lower half of the form. CSAMs gives you the following composite properties. Equivalent Young's modulus in the x direction, EXM, equals 69,564 newtons per millimetre squared. Equivalent Young's modulus in the y direction, EYM, equals 25,375 newtons per millimetre squared. The equivalent Young's shear modulus, GXY, equals 18,585 newtons per millimetre squared. And the total thickness of the composite laminate equals 0.55 millimetres. Now, the strength of the composite is based on strain limitation, and CSAMs calculates the strength in direction 1 as 278 newtons per millimetre squared. The strength in direction 2, 102 newtons per millimetre squared. And the shear strength of this composite laminate, 74 newtons per millimetre squared. Based on these calculated composite material properties of equivalent Young's modulus, strength and thicknesses, an initial size of the intended carbon fibre composite component can now be calculated. Now let's see what happens to the composite properties when we add to the number of the unidirectional carbon fibre layers to make a total of 4. CSAMs calculates the Young's equivalent modulus in the x direction, EXM, as an increase to 86,756 newtons per millimetre squared. Previously, this value was 69,564 newtons per millimetre squared. The Young's equivalent modulus in the y direction, EYM, decreases to 21,598 newtons per millimetre squared. Previously, it was 25,375 newtons per millimetre squared. And the Young's equivalent shear modulus in the xy plane, GXY, decreases to 15,542 newtons per millimetre squared. Previously, it was 18,585 newtons per millimetre squared. The thickness of the laminate increases to 0.746 millimetres from 0.55 millimetres in the last laminate. Now the strength of the composite changes too. An increase occurs of the strength in direction 1, that is Fx, at 347 newtons per millimetre squared. Previously, it was 278 newtons per millimetre squared. A strength decrease in direction 2 to 86 newtons per millimetre squared, which was previously 102 newtons per millimetre squared. A shear strength decreased to 62 newtons per millimetre squared. So we see here, by increasing the number of unidirectionals, there's a tailoring effect, a bias effect if you wish, increasing the Young's modulus in the x direction. But this has a decreasing effect on the other properties, except for the thickness. Let's see what happens when we increase the grams per square metre for the carbon fibre unidirectional from 100 GSM to 180 GSM. Press the execute button, and now in the results box we will see there's an increase in the Young's equivalent modulus in the x direction, EXM, to 99,785 newtons per millimetre squared. Previously it was 86,756 newtons per millimetre squared. A decrease occurs of Young's equivalent modulus in the y direction, EYM, to 18,736 newtons per millimetre squared. Previously it was 21,598 newtons per millimetre squared. A decrease also occurs of Young's equivalent shear modulus in the xy plane, GXY, to 13,235 newtons per millimetre squared. Previously was 15,542 newtons per millimetre squared. Now the strength of the composite also changes. An increase occurs of the strength in the direction 1 in Fx to 399 newtons per millimetre squared. Previously it was 347 newtons per millimetre squared. There's a strength decrease in direction 2, that's Fy, to 75 newtons per millimetre squared from 86 newtons per millimetre squared. There's also a decrease in the shear strength to 53 newtons per millimetre squared from 62 newtons per millimetre squared. Don't forget that the material axis of fibre direction 1 aligns with the geometry reference axis of x. Next we will examine the effects on the composite properties of increasing the GSM for the carbon fibre plus and minus 45 degree layers. Because we are introducing a thicker fibre layer for the carbon fibre plus and minus 45 degree orientation, the directional properties of the laminate will be modified. That is a form of tailoring. This fibre modification will increase the shear strength and stiffness properties of the composite, but will reduce the strengths properties and other properties in direction 1 and direction 2. There is a decrease in the Young's equivalent modulus in the x direction, EXM, to 88,888 newtons per millimetre squared. Previously this value was 99,785 newtons per millimetre squared. There's a decrease in the Young's equivalent modulus in the y direction, EYM, to 18,572 newtons per millimetre squared. Previously this value was 18,736 newtons per millimetre squared. An increase occurs of Young's equivalent shear modulus in the xy plane, GXY, to 16,170 newtons per millimetre squared. Previously this was 13,235 newtons per millimetre squared. Now the strength of the composite will change too. A decrease occurs of the strength in direction 1 to 356 newtons per millimetre squared. Previously this was 399 newtons per millimetre squared. A strength decrease in direction 2 to 74 newtons per millimetre squared from 75 newtons per millimetre squared. And a shear strength increase to 64 newtons per millimetre squared from 53 newtons per millimetre squared. Now the thickness of the laminate will increase to 1.178 millimetres from 1.022 millimetres. The composite laminate now will be heavier than the previous laminate design. Don't forget that the material axis of fibre direction 1 aligns with the geometry reference axis of x. So in CSAM, so many parametric studies can be carried out very quickly, like I've just shown you. The information that this laminate analysis provides is essential for you to start your structural composite calculations, to do your own investigations. In CSAMs, the information behind the purple box is material data that is hard-coded into the software. This data can be changed for the calculation, but what is hard-coded gives a good start to the calculations of composite properties and is good for your initial composite design. So just to summarise, the carbon fibre layup, that is the stacking sequence, which is shown in the diagram, and CSAMs is shown on the right, gives the input and the results data. The results data is shown larger on the lower left. So now we move on to the initial sizing of a simple composite structure. What I would like to show you next is using those composite material properties that we have just calculated to initially size a simple beam. We will use the properties of the carbon fibre that we've already analysed. Let's say, for example, that this beam represents a car structural longit. Many cars are built with a primary structure similar in geometry to that of a ladder. A similar primary structure design concept is also used for trains. There are two parallel structural longits that run from the front to the rear of the car or train, and the rest of the body structure is built up around that. For simplicity, we will assume that our beam transfers 50% of the load of the car through to the two front and rear wheels. We assume that our composite beam is simply supported. The distance between the supports is 2000 millimeters. For the first calculation, we will use a box beam, as shown here. The dimensions that we will try of this beam will be 60 millimeters deep and 100 millimeters wide. The laid carbon fibre composite properties will be used in this process of designing the composite beam. Here we see a generic composite box beam, which is simply supported by two bricks, one at either side. My bricks here represent the wheels of a car. We will open CSAMs to demonstrate how we can initially size the component. We do not need finite element analysis. CSAM contains simple component design and analysis tools based on closed form solutions. Go to SLAMs, which is Structural Laminate Analysis Models, and we will select the top icon, which is Simply Supported Hollow Beam. Write down in the top box a value of 200 kilograms for the centrally applied load. Next, we insert the beam dimensions. We then write in the property values that has been previously calculated. The thickness of the composite laminate also. The material density. In this case, we are using a carbon fibre at a density of 1.8 grams per cc. Because CSAMs will also give you the weight of this beam. Press the execute button, go to the results box. CSAMs has calculated the stress at the outer ply is 248 newtons per millimetre squared. The structural strength reserve factor is calculated at 1.12. Because this value is greater than the numerical value of 1, it indicates that this box beam of the dimensions tried and of the composite properties tried, that the carbon fibre composite beam has sufficient structural integrity to withstand an imposed load of 200 kilograms. It may be that a limiting criteria is deflection or weight. CSAMs shows the calculated deflection and weight. We try a higher load of 400 kilograms on our carbon fibre box beam to see if it will be strong enough. The outer ply stress shoots up to 495 newtons per millimetre squared, and the reserve factor gives a value of 0.55. So in this case, let's try changing the beam depth from 60 millimeters to 100 millimeters. Press the execute button, and it shows that this time the structural integrity of the beam is just acceptable at a value of 1.04. Note that the weight has increased to 0.788 kilograms, and the deflection has increased to over 26 millimeters. Now let's try a different section beam. We'll look at a generic composite C-channel beam, which is simply supported by the two bricks, one at each side. The two bricks represent the wheels. Open CSAMs to demonstrate how we can initially size the component. We go to SLAMs. Select the icon, which is the simple supported C-channel beam, and type in the value of 200 kilograms in the top box for the centrally applied load. Next, we put in the beam dimensions. And then we write the composite material properties that we previously calculated and used for the box beam. The thickness of the composite laminate is 0.55 millimeters. The material density, in this case, we are still using carbon fibre at a density of 1.8 grams per cc. Press the Execute button and go to the results box. CSAMS has calculated the stress at the outer ply at 270 newtons per millimetre squared. The structural strength reserve factor calculated is 1.03. Because 1.03 is greater than the numerical value of 1, this indicates that the C-channel beam of the dimensions tried and made from the carbon fibre composite and its properties have sufficient structural integrity to withstand an imposed load of 200 kilograms. CSAMS is an ideal software to be treated as a parametric tool. Many variations of beam dimensions and properties can be calculated and can be tried very quickly. To summarise, what I have explained in this lecture 4 is the effect on composite mechanical properties by the introduction of angled plies into a composite laminate design. We have looked at two different material type composite laminates. The first was of 2 layers of unidirectional glass fibre. The equivalent Young's modulus and strength in membrane remain the same in this laminate architecture design no matter how many layers of unidirectional glass fibre were stacked on top of each other. Only the thickness of the composite changed. However, as demonstrated in the second material composite type, that of carbon fibre, angled plies of plus or minus 45 degrees were introduced into the composite laminate design. Such composite laminate architecture complies with structural design rules and offers the basis of tailoring the composite for stiffness and strength. I have shown that with CSAMS, quick parametric composite laminate architecture studies can be accomplished to get the initial optimum composite properties desired. With these calculated properties, I have gone on to produce an initial size design of 2 simple beam sections, a box beam and a C-channel beam. At this stage of learning, what is more significant is not the calculations on how to do the above, but the importance of understanding how the mechanical properties of a composite material can easily be changed, unlike that of metals. Please contact me if you would like to inquire about attending a course on composites, or you are interested in an online course on composites, or you would like to attend a one-to-one composite training course. You can see these courses on the website highpeakcourses.com.